today's topics is about deep forward network. So today will be the first, I would say, the first lecture that we delve into the neural network architecture, and then we will take a look at the architecture interplays between the elements in the networks, and we'll see how does it work in terms of the learning of the network through an algorithm like backpropagation. This is like the step that allow neural network um, to exceed everyone's expectations back in 1990s. That it allows the research to establish the multiple work in the field of cognitive computing, pattern recognition, and I would say the revitalization of the field in 90 to 2000. And that is, I think, the spark that results in today's advancement in deep learning. So we will take a look at how does it work in terms of the neural network architecture, in terms of neural network itself, and how do we extend from that point toward the deep architecture and using the same backpropagation to help us in the deep learning work. And so today I have already also prepared this because there will be mathematics part as well besides coding. Right? Working with deep learning requires you to think a lot in terms of mathematical construct and what would happen if you combine those mathematical construct with the data. Right? So when you read the paper, especially in your term paper project, you need to think about this a lot on why is why was the author propose such a model? Right? What are the translational translation between the mathematical claims and the implementation that exist in the paper? And that would be the one of the main goal of the term paper that you have to do. Okay, right. So let's take a look at the basic, and this should provide you with a certain foundations for you guys to go into the deeper detail there. Right. So what is the deep forward network? Right. This is a network. Well, the name with the network here would suggest that this is a neural network, right? And it will be the neural network that compute in a forward manner and can have deep architecture. So the other name of the deep forward network is, well, I would say the old name that is often called is multi-layer perceptron, MLP. Even the implementation in the scikit-learn also use the MLP as the name to define such a deep forward network. Right. Back then when I started learning this, it is often called the ANN, Artificial Neural Network. Right. So this is the feed-forward network. The idea of the network is to approximate, right, get an approximation of a certain function, f star here. Okay, we are going to build an f star here, which the f star here should, in the classifier, should map input x to a category y, right? So we are trying to create a function, right? We are trying to let the system learn a certain function, and that function should map from one input vector to the class. Okay, so it should map the input x with a certain parameters theta. Right? This function should map this into an output y. Okay, theta is a certain parameter that the model has learned. Right? Okay, this is the deep forward network definition. So if we were to write it in draw it in terms of the block diagram, it should looks like this one. That is, you have input x, and then this input x would be mapped with the certain function to the output y. Okay, this is the feed-forward network. There is a certain type of network called the feedback network, or this is called the recurrent neural network. With the different network architecture, this allows the system to perform much more than its capability of mapping. Right? It allows the network to remember the pattern that they had predict previously. Okay, in electrical engineering, in electronic and computer engineering, you can think of similar analogies about these two. Like this can be thought of as something like combinatorial logics, that you give certain logics and then this logic would predict certain output out, just like that. Why this one can be thought of as something like the flip-flop, the logics that contain flip-flop, which means that it should have an ability to remember the state of the existing values. It should have a certain storage of the existing state in order to use that state to drive the output. And that state can be part of the output as well for the recurrent neural network. We will take a look later on, right, on multiple types of network that relies on these two ways, both in terms of feed-forward. This F can be changed into convolutional type to work with image. And why for the recurrent neural network, we can think about some applications like sequence analysis, like in language analytics. In that sense, the output and input can be in terms of the text itself, right? It can be used to perform text classification, emotion recognition. It can be used to perform something like sequence to sequence translation, right? So these are the architectures that can be done here. Furthermore, maybe, I don't know, in the future, you may thought of, you yourself may be the author, you may thought of some other type of architecture that would benefit certain tasks. Because after this course, you will see that actually the idea of many of the invention in the deep learning so far are very primitive in terms of the way that they think about mathematical construct there. But it can learn the pattern based on the ability that we kind of design the system to be able to capture certain part of the data and extract it as the pattern. Like in convolutional neural network, you can extract the convolutional features. In the recurrent neural network, you can use the previous sequence to drive in terms of remembering patterns. And once you see this, that might allow you to think further on different types of architecture that you may come up with your own. And then actually that many of the AI researchers right now think about it this way as well. They're trying to come up with different way to imitate, to mimic human cognitive ability like attention, like transformation. You will see that implemented in the research paper that you study. All right. So now let's take a look at the basic first, right? So the feed-forward network would have network component, right? We call that network because they are the connection. You see picture later, there are connections of nodes. Each node form a computing unit. Think about it as a layer of function. Like you have one function f1, you have three functions f1, f2, and f3. When they are used in chain, right, passing the value passed to one layer, like using f1 to transform x, and then using f2 to transform x, using f3 to transform x. This chain structure can be formed into a structure of neural network F that composes of multiple structures inside. Well, the layer will look like this, but I will just go into the same chain structure first. In this, think about x as input. We have the first layer, which will transform the vector x into a vector after f1. After f1, this will be used as input to fetch to f2. f2 would then transform the vector, output vector of f1 and input vector of f2 to be the output vector of f2, and then use those as input to f3, and then f3 will transform everything to the output. Right? This will be the output layer. Okay, the depth of the network is determined by the number of layers exists here, right? And why the width would depends on the number of dimension in terms of the node, computing node inside the network, right? So how does it look like? Neural network looks like this. Each of these nodes can be thought of as a logistic regression. So one node here receive input from multiple inputs, and then combine them with certain weight according to the line here. Each line would have its own weight, and when you multiply the weight with input and combine them, you get regression, right? regression with activation function inside the node is logistic regression. So each node here can be thought of as a logistic regression, but I would like to think about it as a computing unit. Right? Each node there is a computing unit, a neuron. Right? That's the usual, the old name that used in the ANN definition, that you have the neuron here, neuron, or perceptron when we talk about just one unit of neuron. Okay, and each of these would do the computational, the computation by itself. If we thought of it as a logistic regression, then it would work like this, that it would receive input from multiple features. And then from these multiple features, it would learn the parameters, the weight associated with each features for each model. And then it would learn whether to trigger the output at this stage. If the output is triggered, this will be then used in the subsequent layer as input, so that it would work like you have perceptron, that you have neuron that can decide on its own whether it would be fired, it would be activated or not, based on a certain pattern. So the idea of network learning would be to let the system learn how to capture, how to match input to the output by capturing patterns inside the weight of this computation. Okay. Now let's take a look at the definition. We have input layers, right? These are the, think about it as the column of the data frame that you have. I think that's the input vectors. Okay, just one row means fetching it to one at a time. The depth is counted by the number of layers, right? This is the depth of 4, right? So you can think about the layer of weight here. And you have the output layers which would relate to the output. In the implementation you see later, it depends on the types of output that you want, whether you want the output to be multi-class, binary class, or linear distribution. We need to define those distributions into the model that we try to create. The hidden layers are the layers inside. Usually, as the name suggests, that these are hidden, means that in the actual setting, in the actuality, you do not know these hidden layers, right? But you only see this input and know this output. But think about it as when you're trying to learn something, you see input, you see output, then your brain will make connection between them, and this is how it works inside. All right, so these are the network architecture. Inside each node, let's zoom in. Right? Let's zoom in come later. Okay, so this is the network structure. In the training step, so when I write like this, that you have input vector x, so it's like here you have input vector x at this layer. This input vector x would then be computed at the first layer and form the output of layer 1. Output of layer 1 is f1x. f1x is used as input to f2x. Right? f2x is this layer, and then the output of f2x is used to fetch f3x and so on. Right? This is not a representation of that function, because otherwise you would need to have the fourth layer, which I don't have here. Right? I have 3 layers here. Okay, but well, more or less, yeah, this is how it works to represent things as structure, as layer. Okay, how about the training? In the training, just like logistic regression, we drive fx, right? We try to drive the function to match the f star x, right? To match the actual data. So the training data would provide a certain approximate of f star x. It would provide a certain snapshot of how the function f star x that we want to approximate looks like. And so for each example, we would have the observation x with corresponding label y, right? Pair between them, right? X and y. Then we use this example, right? We use the example to the training. The training set an example specify the output layers of each input, and this will be used with the learning algorithm to train the weight in each layers. How does it learn? We will see about that later on. We will not talk about it now. So subsequent slide will be about why the neural network works in terms of capturing patterns of data, okay, and why using deep architecture would allow us with even more capability in representation of data, in representing the patterns of data. Okay, why is that? Why does it work? Why the deep neural network works? Why the simple neural network works? The key here is to understand the ability of neural network to transform the data from one domain to another domain. Right? It has capability to change, to transform the data from a certain rectangular domain in the other domain that allow us to divide the data easier, allow us to make prediction easier. Okay, how does it work? Let's take a look within the mathematical foundation here. Right? So for each input x, you can transform the input x to another domain by having certain mapping function phi. Phi x will transform x to another domain. Right? Think about this. I think one obvious example with the transformation like this is when you learn in your undergrad class, you might learn the concept of rectangular domain and polar domain, right? Rectangular coordinate and polar coordinate. I think that would be in mathematics 1, 2 or 3, I don't remember, right? But do you need, I think you should, I think you learned that when you learn things about electrical, or maybe in physics class, when you learn things about the in physics that you have phasor, that you have representation in time domain and frequency domain, right? And that for that you need to learn about the polar coordinate and the rectangular coordinate. That such a function is the transformation function. It will transform input to another domain, right? So thinking about it here, it's like we have a new representation of x once we perform transformation. And actually, machine learning relies on such a techniques a lot in many applications. For example, this phi can be very generic function like the RBF in support vector machine. Right? When you learn the technique of support vector machine, you may know that the SVC or the SVR function that you have in scikit-learn has the ability to transform data to another domain. They call that the kernel function. Okay, the kernel function would transform the data to another domain, which allow you to have a hyperplane that is easier, that cut past to the data point. Right, so it can be very generic like that. Right? The phi can be manually specified, like what business analysts like to do. Like they would want to transform variables from one domain to another domain. Like you have the income column, you have the debt column. The econom I don't want to say economists, I would say business people would want to have something like the debt to income ratio. If you work with a company like Kazikon Bank, SCB, this is a parameter that is very important when you make loan application, debt to income ratio. And that is actually the mapping from the data set in the debt space and income space into the debt to income space. Right? So, and that is the manually specified function phi to do the mapping. Or this is what is quite cool for the deep learning and neural network, particularly to use with the unstructured data. You can let the deep learning learn the phi by itself, and that is very important features in neural network and deep learning, because many times when you work with the unstructured data, this unstructured data would be difficult to represent. Well, you can use edge, maybe you can use the gradient, or maybe you can use part of the image to perform classification, to perform regression. But why not using the network that can learn this representation by itself? It can focus on which part of the image is important part, which part is the face, which part is not, and that would be very useful. Right? So we can use neural network to learn phi, right? To learn the function, the mapping function, which will transform from f and then x and then parameters, and you have the phi of x time the weight. T here means the transpose right? When you transpose the vector, you have like from row vector to column vector. So this is like a dot product between the result phi that you have already transformed x to and the weight of the network, and then phi phi. Then you learn instead to find theta, you can learn that by learning the phi, learning the representation instead of having your own representation. And so this is the idea of the deep learning, and that makes deep learning application very interesting, because you don't have to come up with your own feature. What you need to come up would be the way to represent data mathematically, and then implement those way into the model and let the model capture those mathematical construct by its own. That means your data can be simple, your data can be noisy, and the system will handle that by itself. So that's the thing that neural network work. It would map from linear to nonlinear. Let's take a look at example here. This is an XOR function, exclusive OR function. Exclusive OR is an operation that when you have binary values, you have value of 1. If one of the binary value you have two value. If it's like 0 and 1, you get value of 1. If it's 0, 0 equal to one another, you get 0. Like this is an XOR function. Okay, now let's say what we have x and y in forms of the data that looks like this. Okay, we have 0, 0 with map to 0, 0, 1 map to 1, 1, 0 map to 1, 1, 1 map to 0. Okay, now if we were to represent this as let me skip it one slide. I will come back here. If we were to represent that as the picture, it would look like this one. You have x1 and x2, and this is 0, this is 0, this is 1, this is 1. Now you see the problem, right? If you were to draw one line, just one line, can you separate 1 from 0 using just one line? You see that it is impossible, right? This is not linearly separable, right? Because you have 0 and 0 on the opposite side of 1 and 1 like this one. You need at least 2 lines to make classification, to separate 1 and 0 from one another. And this is actually a dilemma that researcher back in, I think, 1920, 1930 found that the perceptron, the neural network that they thought of, cannot learn the XOR function. It is quite a stumble that they encounter. They cannot use network learned that back in 1920, 1930 to learn this type of pattern, to solve this pattern. Then it comes many years later with multiple layers, and that allowed things to work. We'll take a look at that later. Okay, so let's think about this as a regression work, right? Well, it can be classification, but let's think about it as regression here. We need to choose theta, right? That let's theta be W and B, right? W and B are the weight of each x, and B will be the bias. So we have the function fxwb to be x transpose, which is just a column vector x, and transpose you get the row vector multiply with the column vector w. This would be the dot product between x and w, and plus the scalar b. And say, because we will think about it as the regression, the loss function j theta would be the comparison between the actual value and the learned value, right? Minus between them, you get error and the difference. Square them, you get the absolute value of error, and then sum them all, you get j theta as a loss function. This function, if it has more value, it means that it has more loss. Less value, less loss. Means that the idea here is to find theta that minimize this function, right? We need to minimize j theta and finding w and b that would minimize this function. Okay. But well, suppose we solve that directly, we will find that w and b would be 0 and b would be 1/2. Meaning that you get a straight line here as the approximation of this function. You get just a straight line here, which is weird, right? Because Well, we want it to represent the trends, but somehow we cannot. So what happened here? Right? We want it to be able to estimate the value, but it cannot. Why does this happen? Right? This happened because one line cannot represent this complicated function. You need to have a way to transform the data to another domain in order to make the classification of XOR work. This, when you think back to years 1920, before the age of computer, it's quite a dilemma that people try to solve, and it's quite a simple logic to solve. After they solve it in I think 1950 or so, it's still not applicable, right? Just imagine you just have a network that can do XOR, but it cannot do anything else. How would that help? Comparing to a method that comes out in the later year, like logistic regression, you have the SVM, you have decision trees that kind of range in machine learning. And that's why in the early years, techniques like those are the technique when you refer to the machine learning techniques. Neural network is something like a gimmick that people thought, oh, this is a brain model, but it doesn't work. Comparing to random forest, that the other one is better, right? But it turns out that after the invention of the deep architecture, that you stack the neural network in so many layers, it allowed the network to be generalized to, you can say that it can capture any function, it can learn any representation, right? And with a certain tuning and understanding in its mathematical foundation. All right. So now let's take a look at XOR first. Right. So in order to solve XOR, you need to have at least two nodes in the hidden layers. You cannot just have one hidden layer node. You need to have two nodes. How can I? Here, you do have H1 and H2, and H1 would take in input from X1 and input from X2. H2 as well take input from X1 and input from X2, but each of these would have the weight. Yeah, I should use this one. Sorry, should use this. When I write, see all in my head here. So this would have like W11 and W12, W21, W22. Make it well W, right? So these would have an individual weight associating with each line here. Same goes for the above here. You can write it in a simple form as on the right hand side here. The right hand side is notation. The left hand side is like the expanded notation that when you kind of like to write in a full form, but the problem is that when you have lots of nodes, it will be difficult to write. So people tend to write it like the layer model. That is, you have X, go to X will be transformed to H. Based on this parameter W, H will be transformed to Y based on this parameters W, the small W here. So this is like writing it as a short notation. So it works like this one. We have F1x. F1x here would be W, and transpose here to denote that you kind of transpose row and column and multiply with X, and this F1x as a result with C here we give you H, right? The activation at hidden layer. Okay. Now for the Y will be F2 and then H and W and B together with B. F2H would be H times W. So you take H as the result of the earlier layer and then transform it with the weight W to get Y, right? So this is the feed-forward network, right, with one hidden layers and two nodes. And then in combination, you can write as the stacking of two layers, and this would be the big function here, fx, and then these parameters that need to be learned. When you think about it as the linear regression, linear function, linear regression, you can see that the multiplication here, because the function here is linear function, you can think of it as you have w multiplied with the small vector w here, transpose, so that I can represent as vector, column vector, transpose to get the row vector, and then multiply with the multiplication between the weight and the x, which is the activation. And if you combine the weight here to be just one value, you get the w here. This w comprises of the two weight here. The reason that it switched is because of the nature of the matrix. All right, and you can switch it from row to column if you kind of switch representation, the order of the other one. So if you want to check this, whether this is correct or not, I would suggest that you refer to the basic matrix multiplication properties. Right, that's the linear. Right, you can map from that to linear, and yeah, what I want to show you is here in the example, but it's like 2 slides away. Okay. That is for the linear learning, that you can see the stacking between them. But neural network has been used to learn the nonlinear pattern. In order to do that, neural network has to perform transformation of the values, the output. This is done by having some nonlinear function called activation function. Activation function is a type of function like in logistic regression, that you have input coming in. It can have high value, it can have very low value, but it will be shaped into having just the value within the range, like 0 to 1, to denote something like the firing of neuron, right? To denote the detection of the activation function, right? That is why it's called the activation function, to denote the activation of the node based on the certain pattern that it learned. Okay, so in that sense, the XOR we have would be w times x plus c, and this would have to pass to a certain transformation g. But in our case here, g is linear transformation. Okay, but it can be the other way around as well, that g can be nonlinear transformation. The useful and most used nonlinear transformation in the deep learning is the rectified linear unit, ReLU. This is the activation that have value of 0 when the value less than 0, and once value is more than 0, it has value of 1. A good thing about ReLU is that when you dip this function, think about your last example. Remember that when you do things gradient descent with the logistic regression, you have to calculate the derivative, right? You have to calculate the gradient of the error function. And calculating gradient, you need to take a derivative of activation function of the logistic function, which results in its own value, right? If we talk about logistic function in terms of logistic. D of fx, activation function, by dx would be fx and 1 minus fx, right? So this would be the derivative of the function, of the logistic function. But now take a look at the ReLU. What is the derivative of ReLU? And you can see that, oh, this is quite a simple derivative, right? If the value, well, except 0, which is exception case, we will not consider that. If the value is less than 0, derivative of ReLU would be 0. If the value is more than 0, derivative of ReLU would be 1. That means the derivative is, well, something like you don't have to really calculate derivative. Just have to see if it's more than or less than 1. And this would make the ReLU function and the ReLU activation function very fast in learning. A key idea of deep learning is that it needs to learn fast. It needs to have ability to utilize learning algorithm very efficiently. That's why we need to have the GPU, the card to perform the learning, because we need to have an efficient calculation machine, and GPU is one of that. Okay, so this is the function that would map from the linear output to the output, the desired output. Now let's take a look at example here. The complete network of the say, suppose we have already learned that the network. This is the form of the complete network for the XOR. We have this activation function. This is ReLU, and this is the ReLU at the hidden layers. That's why we have W times X plus C. And this is ReLU because if it's less than 0, it will be 0. If it's more than 0, it will be this value. And plus B, this is an intercept. And here, this whole thing is multiplied with W here to denote the final layers, W. Alright? So let's assume that we already have the value learned, that we have W here equal 1, 1, 1, 1. We have C at this H1 and H2 equals 0 and minus 1. And we have W here equal 1 and minus 2. So let me note here in order to, for you guys who come later into the class, and then you may want to see it noted down into this. So here is 1, 1, 1, 1, and C, which is associated with C equals 0 and C equal 1. Right, these are associated with the hidden layers. And then the final one would be the 1 minus 2 here. Okay, this is a completed group. Now let's see how does it work if we were to input here, and then we will see why the neural network works in terms of data transformation. This is very important to understand deep learning. For the input, we have the input in its own domain as 0, 0, 0, 1, 1, 0, and 1, 1. Right? After that, you need to multiply input X with the weight. Multiply it with the weight. We have each row here. Multiply with the weight. Right? The weight is 1, 1, 1, 1. So what I'm going to do here is to should I? Well, I will do that and then think about it as something like extension. I'll just put 1, 1, 1, 1 here, and then you can think about multiplication. So here 0, 0, 1, 1 equals 0, 0, 0, and 1 equals 0, right? And then 0, 1, 0, 1, 0, 1, 1, you get 1, 0, 1, 1, 1, you get 1. Right? That's for the 0, 1. Next is 1, 0. 1, 0 and 1, 1, you get 1. Because 1 and 0 take with 1, 1, you get 1. 1, 0 with 1, 1, you get another 1. And 1, 1 with 1, 1, you get 2. Right? So this is why for the X times W, we get this matrix. And then we can then add C. Now let's get back here and see. C is 0 and minus 1. Right? As the 3 transpose, which because we have 2 nodes, and the data for right now is like each row would be the result of the H layer. Then we have XW plus C. So plus 0 and 1. 0 is minus 1. That's why we have here 0 minus 1 and 1 0 1 0 2 1. Now this is interesting. Let's compare these two. You can see that the below matrix, right, the matrix below, is the result of certain calculation of the matrix above. That means it is a transformed version of the matrix above. We can write it like this one, which we will see later. Now this is not the end, right? Because it required to go through another thing. It's required to go to ReLU, and ReLU would kind of marginalize, so would kind of fix the value that is less than 0 to be 0, like this. And then finally, if you were to multiply W 1 minus 2 here, we get here 0 0, you get 0, 1 0, you get 1, 1 0, you get 1, 2, and 1, you get 0, right? This is the result. But interesting thing is to take a look at this. Take a look at the transformed H space. Let's compare this H space 0 0, 1 0, and 2 1 with this one, right? With this one, with X. For X, we have this as the original X space. That is, we have 1 and 1 here, and 2 and 0 and 0 here. But now if we take a look at the transformed space after the first layer, we get 0 0, 1 0, 1 0, 2 1, which are here 0 0 and 1 0 and 2 1. But 0 0 is 0, 2 1 is 0, and 0 and 1 both are 1 as a result. Now, from this learned H space, you can now see that you can draw a line, and that line would draw a simple line, and that line would separate the data into two parts, right? So this is how the model can learn to separate the data, and then it can transform the input data into another domain, and that domain allow you to easily map between them, right? Map or perform the task between them. Okay, how do we learn that? Well, I'll go past through this very fast, right? You learn it through the gradient-based learning, just like what you did in the logistic regression. So in that sense, it means that you need to define the cost function or the objective function or the loss function, right? Or I usually call that, in machine learning, we usually call it as the loss function, because we are trying to model the data, and the loss occur when you cannot model the data. In optimization, you call that objective function, right? The cost function is also in the machine learning discipline, but well, they are the same, right? Then we choose the parameters that best represent the model according to the input and output data. So how do we define the cost function? Okay, you have already seen how do we do that in the last lecture in basic machine learning, whether it is the MLE criterion or the MAP criterion. So here we do it similar to linear model, right? Defining the likelihood, log likelihood of the log of P and then Y given X, and because the P of Y given X here, in classification it will be the cross entropy, right? So we can represent it as this, or as you can see in the gradient-based optimization lecture, that we can represent it as the gradient as the error between output as well, right? Take the actual output and then minus the one predicted by model, compute the size of the norm, then we can use that as a representation of the loss function. Now it depends. It depends on the type of output that you want, which will make the P model of Y given X differ, right? It depends on what types of model that you have. If the model that you have predict actual real value regression, right? We need to use the linear transfer function, or sometimes it's called a Gaussian distribution output, okay? And that would make the results in terms of the MLE criterion to be the normal distribution of Y and Y hat. Like predict Y based on the parameter mean should equal to Y hat, certain output, and have the fixed variance, right? So this is the log likelihood will be normal distribution. So this will be make it mean square error, just like what we see in the lecture, in the last lecture. Right. So basically, if your output is a real value, right, you can use the linear output. If your output is the normal distribution real value, you can use the linear output layer to represent that value. If your output is a class, then you need to use this Bernoulli output, or the in our case we use the sigmoid, right, to represent the Bernoulli distribution, right? Because the sigmoid can produce the value between 0 and 1, and then by having the output to be the sigmoid means that you are trying to predict the probability of being in the class 1, just like what you did in the logistic regression homework. Okay, so this sigmoid should be used. This is the sigmoid function. Take in the linear combination between the activation. These are the activation mapping and the weight, right? Multiply the dot them together and then add with the intercept. Put that into the sigmoid function. You get the mapping as the result. If you perform multi-class classification, a multi-class, right? Multi-class means that you have multiple output. What to do? You can use the softmax, right, for multi-Nulli distribution. In the multi-Nulli distribution, it's like the task that you have to pick one class out of, say, n class. Like what I'm working, consult the company right now. I have to create a model that predict one class out of a set of products that the customer like to buy, right? So that is predicting one out of the rest. That is the multi-Nulli distribution, and to do so you need to have like a softmax to be the output layer, right? How does it look like for the softmax? Actually, it is very similar to logistic regression. Now think about similar to sigmoid. Sorry, yeah, it's the same. Similar to sigmoid, because in the sigmoid you have just two classes, so you have like exp of a certain class and then 1 minus 1 plus exp of another class, and you divide that and you get just one sigmoid function. But now in a softmax, in order to normalize every output to be 0 and 1, how to do that? Because there can be a negative value as well. So the mathematician came up with the idea that you can just take the exponential of the value, because exponential can never be negative, right? You can take exponential and then divide it by the sum of all exponential of all classes, and then combine them together and then calculate in terms of the fraction, and you get the softmax function, right, which can be used to calculate the probability of the output. That means when you create a model, if you want it to be multi-class, specify softmax as the output. Okay. Right. So it likes logistic regression. When you take the log of the softmax, you get the value of the softmax z. You get the value of z here, and minus log of the exp of the other class. That means if it is likely to be in that class, you get z equal high value, and log here would be low value, right? Log of exponential of low value, and then you calculate the log will be very small value here. If it is wrong and it belongs to another class, this value will be large and it would make this go to negative range. Okay, so correct prediction, you get value of C1. Incorrect prediction, you get the negative log instead. That means you can use this in order to estimate, to say if you make a negative prediction, incorrect prediction, then you will get penalized with the log part on the right hand side. Okay, so these are the output layers that you can choose from. And actually, there are many more depending on the application, but these are the two commons and then the one that we use here in the lab as well. Right. So those are the output layers. We have seen the output layers. Now let's step back a bit. Take a look at the inside. Let's take a look at the input unit. Right. The input layer is quite active research right now. Right. It can be in many forms. The rectified linear unit are the choice that people often use. Let's indicate otherwise. People often use this rectified linear unit as the activation function. and it would kind of take, unless indicate otherwise, it would take the vector of input and then multiply with the weight and to learn the next layer, and then using the something like value as activation function. Okay, so when you work with the network, what are the design choices that you have? You need to determine how many that you want to use basically, and what kinds of activation function that you like. Mostly you can define it as ReLU, but lately there's a trend to use something like leaky ReLU and others, the activation function that they come up with. Right. So, but well, in any case, these are still active research. You may come up with a better one that allow you to learn things better. For example, Google come up with the hidden unit that contain no unit. They call that the residual unit, that the residual line that can link between layers. Right? That's just something simple like that. And it turns out that it's very good in terms of allowing the network to learn faster. Okay. So yeah, when you read a lot of literature in this field, you see that a lot of techniques are very simple, but they just discover things. So this is still very active research, and that you can kind of come in and then get your name out. Now that there's this, why not using sigmoid in hidden unit? Why not using it instead of the ReLU, right? In for hidden unit, well, you can see that it should work. The problem with the sigmoid is that sigmoid can saturate very fast. I will show it. No, not here. Sigmoid can saturate very fast. Let me draw a picture here of the sigmoid function. Right. In the technique like gradient descent, you rely on gradient, right? You have to rely on the gradient to know which path to go. For example, if you are about here, you know that okay, you can go up or down because the gradient still has high value. But imagine that if your value is about here and you want to make change in terms of shifting the value to the other side, this will be difficult because the gradient at the end here would be very small value and it can be negligible even, right? So this will make the gradient learning very difficult when if you use gradient for the internal unit. And remember, those gradient will need to propagate or send back, which we will see later. Right? It will be sent back to the from the, it will start from the output and then propagate back to the input. If on the way to the input it's stuck at a very low gradient at some point, this will make the network unable to learn the pattern, and this is not a good thing. Okay, right. So now let's take a look at the design. Why do we need to have the deep design, right? In terms of the architecture of the network. The word architecture refers to the structure of the network. Usually it refers to how many units or how many layers that you have. Neural network usually arranged in layers. You have multiple layers that are in the chain structure. You will see that in this class later on that the design can be a crucial choice that allows the system to learn different type of patterns, especially when we take a look at it, the advanced architecture. And the RNN, you see that in the RNN, the design means everything because the application that you use depends on the design that you use in order to let the RNN work. Okay, for this one, the deep forward network doesn't really matter. It's a feed forward network, so you can arrange it to whatever you like. So here in the layer means that you have X fetched to W at layer 1 with B of layer 1 activation, and then you get H1. H1 is fetched to second layer, a weight of second layers, and B, and then the activation, you get the value output at the second layers. How many layers do you need? There's a I would say the theory proposed by Honeck in 1990 that suppose if we take the feed-forward network and say that you have a linear output layer, and you have at least one hidden layer with any squashing activation, means something like logistic regression or the sigmoid. You can approximate any, well, Borel measurable function is a mathematical term. Think of it as any function. You can estimate any function that map from one finite space to another, right? So if you have two layers, and then you have like just one hidden layer, right? One hidden layer, you can map to any output between them. Okay. So this is the theory by Honig, and he has proved in his paper that mathematically this makes sense, right? If you are interested in the detail of this, I would suggest that you try to find the paper, and they are publicly available there, so you can take a look at that. Okay, now if we what can we interpret from that theorem, right? In the feed-forward network with single layer, if you have sufficient representation of node, you can represent any function. So if I were to write here, it's like, suppose that I have input layer, then if I have like infinite node here and output, say I have just one output, multiple output to do, then well, you can create any function from the mapping between them. Well, you can think of individual mapping in this case, right? You can create a mapping for sure if you have like infinite node in the middle, in the hidden layers, right? So, okay, that means if we were to have like infinite node in a hidden layer, you can generalize the mapping to any function, okay? But doing so would make this network infeasibly large, right? It would be very large in that sense. So the idea how to solve this problem, it's good that it can learn any function, but what good is it if it cannot be run? There is the idea to having similar capacity, but with a smaller architecture, and it achieved through having a deeper model. When you have a deeper model, the infinitely large here can be expanded in the deeper sense, and it will reduce the amount of the error that occur from the generalization part. How does it work? Let's take a look at this. This is from Mongkut in 2014. I think this is very good explanation, just like the wormhole explanation that you have like a paper tagged together and then draw one from one end to another, and this is quite good for the deep learning as well. Suppose you have the data looks like this one, and you can see that if you were to classify them in the normal domain, you need to have a very complicated layer here. How does it work for the neural network to simplify things? Okay, so having a deeper model, meaning that you have an ability to fold the space into another domain. So here, if the network detects that this is the best way to fold the space, you can fold it for this part of the paper into another part of the paper, and that you can see that the classification is still perfect, and then you can still have this. If you were to fold it again, you have this one, and you can see that the line is a lot simpler, and it can classify the data into two parts. This is how deep learning works, how the deep architecture works. It works by transforming, learning the representation, learning the line here, where to fold the data, so that it has better representation in the separation between the data point. Okay, I would say almost all the technique in deep learning, right, relying on this type of core concept in terms of the transformation. Okay. So once you have a deeper model, in terms of the ability of the model, it would make the model able to learn complicated pattern. This is the result from the number classification transcription from photograph of the address. When you have a deeper model, the model can have higher test accuracy, right, if you have a deeper model in that sense. And also the deeper model with the right structure would allow the model, allow the system to have, uh, to I would say, having better result while having comparable number of parameters. So in the fully connected one that we are looking at it today, uh, if you if you increase complexity of the model a bit, you can see that there is no incremental in the error in the accuracy. Comparing to convolutional network, right? When you increase the number of parameters, the test increase to a certain point, but it dropped. This indicates overfitting. But when you have deeper model, means that the model would have a sparser representation. You can learn deeper representation. Your model would be able to contain similar parameters here, but having higher accuracy. All right. So it means that with the deeper model, the model has less chance to overfit. It would have, but well, that comes together with you need to have enough data as well, and you need to have the right learning algorithm for this to work. But in most cases, deeper model would allow you to be able to capture data in more complicated sense. So how does it work in terms of learning? Right. To learn the pattern, you need to use the technique called gradient descent, which you have already seen. I'm going to just explain it in these two slides in terms of the algorithm. First, you need to perform forward propagation. Forward propagation, think about deep learning as something like a network of light that connecting input to the output, and then that has to need to learn certain resistance of the line, right? So you need to fetch the input and then let the weight to be learned. Right? So here for propagation, right? Moving forward means that you already have here you have a structure W, depth W, and depth L. W is the weight and B is the bias at each layer. X is input, Y is output. So for propagation works like this. You use X as S0, and then for each layer just multiply W with H and add B of that layer. You get A. Put A into activation function to get H, and then keep doing that until the end. You get forward propagation results, and the result here is the predicted output at the current weight. So if I write it here, it would look like this. Say you have two output. I don't remember which I need to write. Okay, the forward propagation works like this. It goes from the input to the output. So it go from the input and then compute to the output. So you have input coming in, and then it goes step 1, step 2, iteration 3, then you get output here. That's forward propagation. Then after forward propagation, you need to perform the back propagation at each iteration. Back propagation would be used to estimate the gradient of each weight, and then you can use those gradient to update the weight. So after the forward computation, you need to compute gradient at each weight, at each edge. So let's start from the end. The end, you have the loss of y hat and y, and this loss, let's say, to be put to g, and we can then do the backward iteration from L back to 1. Then you can convert the gradient to the thing that you need to update the value, right? Use the gradient, compute the gradient, and use it to update the weight and bias, these two. Then update the weight and the bias. Afterward, you can then assign the gradient, compute a new gradient to like multiplying W with the gradient at this layer, and then set it as G, and then let it repeat again. That would make the gradient of the end backwardly propagate to the input. So we have like gradient here at the output first. This comes from the loss. Then after we get the weight, you need to have like the delta of what should I say? The delta of B at this layer and W at this layer. We can then propagate G to this layer. It says this is like G0 and this is G1, and then you can think about it that way. We will take a look at this in example at the end, right? This is how gradient work. So this is basically the same gradient descent, but instead of having just one layer, you need to propagate the gradient from the output layer back to the input layers. I have a clearer example at the end. So let's see how this would work in a simpler. How this work? Well, we have in the detail we have input x multiplied with weight and then sum them all and then fetch it to the activation function and get the output y. In your lecture number 3, right? You have to write a function to optimize this function, right? Optimize the sigmoid function. Activation function can be something like sigmoid, or it can be like on off. It can be like the ReLU there. But let's stick with sigmoid here. Sigmoid looks like this. The good thing about sigmoid is that when you calculate the derivative of the sigmoid, the output of that derivative is simple. It's just the sigmoid value multiplied with 1 minus sigmoid value. Okay, it's smooth like this one. And that's the thing that we need to estimate. Now let's try to see how to estimate that in the data. And actually, you have already implemented that, hopefully. Otherwise, you need to submit it tonight. Okay, and I'm still lecturing you here, but you need to submit it before the midnight. If you cannot make it, you need to have good excuse there. Right? Otherwise, it would not be good. In any case, I would not recommend not submitting the work. Right? Submitting partial work is better than not submitting the work at all. Okay. Yes. Well, just you need to show me the code anyway in the implementation. Your friends asked whether you need to submit a Python file too. I would say that because you need to show me the code implementation, so why not? You can submit the notebook actually. You can do the whole thing in the notebook, just one notebook, and print it out and submit to me. That's it, right? So if you ask me whether you need to submit the code, then the simple answer would be yes. Yes. Mathematics part in the Jupyter notebook, that will be tricky. Yes, you can do it handwritten, and then you can add it to Jupyter. You can print things out, doing it in Word, and then combine file later. I'm really flexible there, whatever, right? You can try to find a way to submit. You can just combine them into one PDF. You can attach them and make reference. You can use LaTeX in Jupyter. Quite tricky, but fun, right? So figure it out. I'm okay with all. Just submit the work in any case. All right, now come back to here. After this, we will take a short break and then having I'll show you how to work on the deep forward network with Keras. Right. So how do we get the weight? Right. The weight comes from training. Okay. For the training data, you have to have certain training data, which for each of the data point, it will be used to modify the weight to get a better result for each batch, if not data point. For each of the modification, when you go through the whole data set, We call that one epoch. An epoch is an iteration when you're trying to update the network with all the input that you have. Usually you need multiple epochs to train the model. Okay, and how to train the model, right? So for example, you have the linear transfer function. The training would be the same way. Well, I would think that all these things is the same as the gradient optimization. So if I were to tell you how do you learn perceptron, I would just say that you use gradient descent, and then that is the thing that we use. Right? So we need to update get the new weight from the old weight plus the learning rate and the derivative of the error function, which is the difference between output and the desired and multiply with the input. That is for the linear transfer function. You can prove that yourself here. For the sigmoid, this is what you have to derive out anyway, as I suppose in your assignment. Right. And then what would happen in terms of, suppose that we have linear transfer function. What would happen in the calculation? Linear transfer function and then deciding the weight later. Say that suppose we have 1, 0, and 1 with the weight of 0.5, 0.2, and 0.8. And then and the result here is 1 because if we have 1 times 0.5, 0 times 0.2, and 1 times 0.8, you get 1.3. Right? 0.5, 0.2, 0.8, 0.7 plus 0.8 is 0.15 actually. No, I'm wrong here. Let me fix it first. It's 0.15. And suppose let me finish this example one and I'll come back to the question that you have. Okay, this is 0.15. Assuming we have the threshold of 1.2, then it means that the output is 1, correct? But what if the output should be 0 instead? Then let's see. If the output should be 0, but instead in this case it is 1, we can calculate the gradient of each one. Can update the weight here. This would be 0.5, it would be 0.8, and this would be 0.2 in the old weight. And then plus the learning rate, let's say it is this learning rate is alpha equal 1, and the difference between the difference between the what actually has to be and the output the current output and the desired output is 0 minus 1, right? This is the difference, and the input is 1, 0, and 1. So once you calculate this, you will see that if you get 0, if you make mistake, but you does not contribute to that mistake, you will not be penalized. But if you make mistake, and you are contributing to that mistake, you will get learned or here penalized. And then this is a process of gradient descent, as you can see, and we can find a way here after updating this. There should be a way that we can transfer the error here, 0 minus 1, back to this node, so that we would know that the error at this node would be like 0 minus 1 times 0.5, because that's the contribution of error. So by multiplying the weight with the error, you kind of propagating the output back to the input. We will see that later on in the learning part. Okay, let me answer your friend here first. Your friend asks, when we try to do such transformation like WT, C row equals C, X row, every case we should have matrix size compatible multiply or addition, right? Which slide you are referring to? The WT dot capital WT. Which slide you are referring to? Slide number 7. Number 7 or 12. This one. Or what is the question that you have here? Should so what can you repeat the question, please? When we try to pass input data with x and h parameter, we should have the same size of matrix. No, we don't have to. In this case, it should. In this case, right? In this particular case, it should be equal. In this case, it should be equal, but it doesn't have to be equal. Like, let's say you have input as 3 node, and this is 2 node, right? So this means that the input has well, it will be 3, right? And the output would be vector of 2. So if the input here is something like 1, 0, and 2, activation can be just 2 value, like 0.5 and minus 0.5, for example. And then you can have another layer like that. You can see that it doesn't have to be equal. But why does it and your next question is, if not, how to solve those problems? What problem? Because if you it doesn't have to be equal, because if you multiply, let's say, suppose that I have say something like this one, and then I have the transformation matrix that looks like this: 1, minus 1, 0, 0, 1, 2, say something like this. This is the weight at this step, and if I say this is x, small x, this is w, and then I calculate something like w transpose x. This would be 1, minus 1, 0, 0, 1, and 2, and multiply with 1, 0, and 2, and then this would equal to it would be 2 row, just 2 column. It would be 1 and 4, right? And this, the dimension here is 1 times 3. This is 1 times 2, similar to this point. Is this answering your question? Yeah, so it doesn't have to be It doesn't have to be in the same number of dimension. The reason I use this because, well, for XOR it has to be something like this for the simpler version. It doesn't have to, alright? Okay. Now, right, so that's the where right now, okay, here, right? So this is how you update the weight, right? So it means that for each of the instance, when you encounter the error here, you can use the error to update the weight, and the weight can be updated for the whole network. Now, the situation here is that you would have multiple values. So you would have multiple input and have a multiple hidden unit that calculate to multiple output. We call for this one is the extension from the simple perceptrons, and we have the multiple layers with multiple hidden unit. Here you can have this is just one hidden layer, but you can have like multiple layers. Activation is not just a threshold. It can be sigmoid function, it can be ReLU function, and this can be used to model any type of function. Information for the feed forward or the deep forward network, information flow from the input to the output only. But in the latter lecture, you will see that information flow can come back as well to get the recurrent neural net. Now let's take a look at how to calculate that. Suppose that these are the parameters that the model has already learned, right? And you have bias here, and bias at the output. And let's say we use sigmoid function for all of these to see how the classification of XOR would work. And we have 0 and 1 here. 0 and 1 will be fetched to the input node. Then the input node here, 0 and 1, will be used to calculate H1 and H2. So at the H1, we have 0 here, 0 times 4.83, and here at the input 1 times minus 4.83, right? And then minus 2.82. You get minus 7.65 at the output of this stage. Minus 7.65. And for H2 takes 0 and multiply with minus 4.63 and take 1 minus 4.6 and sum them, and then minus 2.74, you get 1.86. And then finally, and then these two has to pass through the sigmoid, and you can see that this get into the value of 0.000475, and for this one it get to the value 0.8652. This one has very low value, this one has very high value. This indicates a certain activation that occur once we pass the input 0 and 1 to the network. That means H2 is activated, H1 is suppressed. And then this activation pattern is used to perform classification later. It's used to fetch be used as input to another layer. You get this small value multiplied by 5.73, this value multiplied by 5.83, and then add the intercept of minus 2.8 here. You get 2.1 something, and then fetch to the sigmoid, you get 0.89, and this can be regarded as 1. This is how it is calculated in the forward manner. Right? When you fetch the value in, then if you perform calculation node by node, this is how it works. But there is a better way in calculation, which is the use of, let me go back, which is the use of metrics. This is a better way in calculation. Rather than do the work one by one, you can multiply the matrix, multiply x with matrix W, add the matrix C to the matrix XW. because matrix multiplication and addition is quite fast, and GPU is optimized to perform fast matrix calculation. And this allows the GPU to be able to accelerate the deep learning model a lot because of the ability to multiply the matrix. Okay, now let me come back to this. So here, let's take a look at backpropagation. Right, backpropagation is a form of learning algorithm, just like gradient descent. It is actually the backbone of it is actually a gradient descent, but it is something like a step-by-step gradient descent. So how does it work? It works like this: that we start by initially set the weight to some value, can be random, can be certain fixed value, and then for each example or for each batch, we will compare the O, the output of the network, and the T, the target, and calculate the error T minus O, and then use this error T minus O to do the backward pass to calculate delta W of all weight in the hidden, of all weight in the input, and then update the weight, just like that, right? So calculate forward to the output, calculate the error, and then calculate delta for each node backward in the backward fashion. And that's how you get it. I have example in this few slides, and we have example there. So once you get the error, right, you can propagate it back. The calculation of error would flow backward. That's why it has the name backpropagation. And once you have that gradient of that error ready for each of the weight, you can update the weight by minus the learning rate, and then use the gradient to multiply with the learning rate, and then you get the weight updated. Doing backpropagation you can encounter the problem, like you can encounter the situation that you have the rate or learning rate to be too small or too large. Right? It can be too small, too large. And how to solve that problem? That is a way to solve the problem by using something like momentum. That is, you can say that the gradient, right? Instead of using the gradient to update the weight directly, you use the gradient to update the actual gradient. This is actually something that akin to exponential smoothing. In exponential smoothing, you would smooth the signal based on the previous value of the signal. So that means that here, beta here is the weight of the gradient of the O value, and then this would be shifted. This would act like a momentum, and then the new value coming in, it will be used to update this value instead, and then we use the whole thing to update the new weight. So this would work like this exponential smoothing would work like a low pass filter to reduce the variation in the gradient. You see a lot more variant of the learning algorithm and the option that you could use of the new name, something like the Nesterov, the adaptive moment. You see that in the latter lectures. I think in the next lectures or so, you learn about the learning algorithm that you can choose to use. Right, and so in the backpropagation, let's see if we have the output and the hidden neuron. We can calculate the error. This is the target minus output square, and then at each stage, we need to calculate the partial derivative, just like in the gradient descent, right? By derivative of this, you put 2 down, and then you get target minus output, and diff of the output, because you have like the function which contain the parameter you want to take a diff to. That is the f parameter here, and then diff of the inside again, right? So we can separate that into diff of the inside would be the output of the layer I, which is actually the input of this layer. Okay, so here we can form this as delta J. This is the part that relates to the error of layer J. This part of the output layers will be used to form the gradient. Right? This is curl E by Wji at the output layer. So if I were to write here, let's write like this. Okay. E is the target, right? And delta J, delta J is here. And then delta J would take the, note that it takes the output of delta I, which is actually here. Output of I, right? That means to update these two weights, right, you need to take the output of layer I and then use that output to update as the input of the next layer to update the value here. Okay. For the hidden neuron, I'm going to change the color here a bit. For the hidden neuron, you can see this part. This is delta K and WK. This is actually the delta at this layer, the delta of the next layer. This is the delta here. This delta would be distributed back here. And because it now has just one weight associated with that, the delta here would be the delta of the WKJ and the delta, this is delta K at the next layer. So this would be the delta at this layer and then propagating back by multiplying with weight. So you have the delta here to multiply with weight to represent the delta at this node. And the delta at this node will be multiplied with the F prime net, which is the result of this node, the partial dip of this node, and multiply with the output of layer I, which is the previous layer, right? So this would be the output of layer I again, right? So doing this layer by layer would allow you to learn the parameters required for updating the network, learning the gradient. Okay, this is how backpropagation works. I will show you how to do that in the number, which is easier to understand than in just the equation. Let's say we have all the weight equal 0.5, and then we have the input of S1 and 1, and the weight is 0.5, so 1 minus 0.5, we get this equal 0.5. Passing through this, we get 0.622, and then this 0.622 passing through the sigmoid again, we get 0.65 and 0.65, but the supposed value should be 1 and 0. How do we update the weight in each layer? Let's see. First, we need to have this. This is the error one. The error one comes from 1, this is E1, this is equal 1 minus 0.5 equals 0.35. So I would write here, right, we have 0.35, and the delta to 1, this is the error of coming from the partial derivative of the output node 1 layer 2. This is 0.65 times 0.65. Where does it come from? The 0.65. The 0.65 comes from here. This is the 0.65. Okay. So this is the output times 1 minus output times 0.35. 0.35 is the error here. Let me draw it here so that it sticks. Alright. That would create this delta 1 on this delta 2 1, layer 2 node 1. Okay, now we have delta 2 1. We then do the same thing for the second node, delta 2 2. This is again 0.65 and 0.65, and this is the partial derivative, and the difference between the error and the actual is minus 0.65 because this is 0, error here, error 2 is 0 minus 0.65, and then you get delta 2 2. Okay. Then from this we can calculate the delta, the gradient of the weight of 211, layer 2 mapping from node 1 to node 1, which would equal, I'll use different color here, equal the learning rate, right? So please, it's hard to write here, right? Learning rate. And this one is this one, okay, and 0.22 here is the input. I would say do the same name here, input at the layer I, input of the preceding layers, which is this value 0.22, and then we can use that to update the weight of the node of the edge W211, right, by just adding that value to this. All right, actually minus that value to that weight. How about W111, the first layer? How do we do with the first layer? Let me change the color to blue then. For the first layer, we need to first propagate. This is the propagation. Propagation. This is the propagation. Because if you look at this one, you take the delta 21 and delta 22 multiply with the weight, which the current value is 0.5. So if I were to write it in here, what happening is actually the error here, delta 22 passing through here to accumulate at this point, this as well coming here and form the delta 1 1 here, delta 1 1. Not just that, it also multiply with the 0.622 and 1 minus 0.622, which actually are the same as the preceding layer, which is the dip of the output, right? And multiply together, you get delta 1 1, which equal to minus very low value here. We use this value together with the input 1 to calculate the weight. So you can see here how the error propagate back, right, from the output to the input, hence the name backpropagation. Okay, so in the backpropagation, all the weight will be calculated in this way, right? After the weight updated, all the process will be repeated, right? Doing the forward calculation, calculate delta value, propagate it back, and update, and then we keep repeating that throughout all the examples, that all the data samples that we have, and in multiple epoch for that. All right. Yeah, so this is all the theoretical part of today's lecture, right? Let's take a break for 5 minutes. I will grab some water and a bit, and after coming back, let's see on how can you implement this using Keras. I have multiple examples to show you. Maybe I'll just show you at least some of them to get a gist of how the Keras work. You can then work on that later on. We keep using Keras in our class here, right? You have a choice. You can choose Keras to work with deep learning, or you can deciding to use something like PyTorch. It's also fine as well as a framework to use with deep learning, right? So this is how backpropagation works, and we'll see in 5 minutes how the coding would work in this regard, right? Let's take a break. Okay. Let's take a look at how to create the deep learning model. I'm going to go through it pretty fast in the data loading and the authors, all right? I'm going to briefly explain how it works a bit here, but we will focus on the architecture of the model. Right. So the first part here that is that I used Keras. You need to install Keras on your computer. Keras is a framework, a deep learning framework that kind of encapsulate the um, TensorFlow inside. So in its mechanism, it uses TensorFlow, like Google TensorFlow, and Keras provide you a types of nice interface that you can create a model. You can flexibly specify the model architecture. Actually, the author of this book, Deep Learning with Python, the author here is actually the author of Keras. So you can see how it works in detail in this book. I think we have, right? So you can search and find the online material for that book as well. Okay, so here I'm importing the IMDb data, right, which is the data to perform the binary classification. It's the to classify the comment on what type. So these are the trained data. This is the numerical code of each of the words here. If you want to decode the content, you need to get the word index and then create a lookup. And then you can then decode the text by doing the lookup here. Yeah, so this is Big Book Bad Music, and that's why it's got rating equals 0 here. Then what we need to do here is to prepare the data from the number here into the one-hot back-upward model. In the one-hot back-upward model, you need to take the sequence and then create the a vector of word. That means in the back-upward model here, what you need to have is something like this. The row here would be document, and the column would be the word, and the value inside in this would be whether you have the word number 1, word number 2, and so on. This could be 0 and 1, 0, 0, 0, something until you get the word 1, something like that. So it would be the word vector, right? The vector of word. So that's why we need to have something like the vectorized sequence down here. Okay, so in the data preparation, we will do the one-hot backward. So data here, data 0, you have 218, data 1, 189, the data are not equal, and you get about 25,000 row of data. And so here I create the vectorized input, vectorized sequence, which will take the sequence and then vectorize it by just initialize the number of 0 here, and then vectorize it by setting the element to 1. If the sequence is in the vector, if the value is in the vector here, just set it to 1. And then perform that with the train and test set. That would make the result looks like this one for each of the train and test. And to ensure that it could run in the computation, we'll just set it to a number, right? Just that. Now is in terms of creating the model. There are two ways to create Keras model, basically. Right? One of the ways is to use the sequential part. The other is known as to use the model API. Right? You can take a look at the Keras website to know more about how to create the model API. I will show you in the later stage on how to use the model API to create the complex architecture. But for this one, let's use a simple sequential model. Right? In the sequential, you can think of sequential as a queue or as a layer. You are stacking one layer and then another layer and then another layer. You are stacking layer to layer. So we need to start with the input layer, creating a model sequential, a blank model, and then add the input layer. This input layer need to have input shape equal to the input vector. Since for each of the row here, it has the dimension of 10,000, we need to set input vector shape here to 10,000. And here we set the activation to ReLU, set the hidden states to be 16 hidden states. So if I were to write here, This would be something like this one. Input here would be 10,000, right? 10,000. And this would map to the size of 16. You can think about the line by yourself. So many lines. And then another 16. And then finally back to 1. So this is how it looks like for this one. And this one use Lelu, and then sigmoid. Okay, so this is the translation of this code. We have the architecture that looks like this. Right, let's create a model. And here I show you the model summary, which will give us the glimpse of the model in terms of the output shape, the number of total parameters, which is 16,000. Is that right? No, 160,000, because we have 16 times unit of input shape, so it's like 160,000 plus 16 come from the number of node here, and then we have like a bias parameters. And for the next one, this with 16 times 16 plus 16, so 72. And lastly, this is 16 plus 1. We get the final layer. So in total, there are 160 parameters. So it's quite a lot of parameters to learn here. And we will train the model using the optimizer called RMS prop. You will learn that in, I think, the next lecture on these algorithms. Using binary loss entropy, you already know this in the previous lecture, the J theta, right? The cross entropy. For the logistic regression is actually the one that you work on right now. You have already finished it. And the metrics that we use to show the results, we use the accuracy to show the result. Then let's take a look at the training part. In the training part, we separate the data into train, right? And validation, and train data. This is validation data, train data, validation data, and train data. Right? You can opt to do it this way, or you can specify the CV doing the cross validation in the model.fit. That's fine as well. Right? Or you can fix the validation with this method. All right. And in the model.fit, I use the partial train and partial Y train to train the model, and the validation to fix to the validation, and say the batch size is equal to 100. What does that mean? Instead of updating the parameters one by one, we calculate the gradient using 200 samples and then update it once, and another 200 samples and then update it another time. Once we go through everything, that is one epoch. So if I were to run this one, yeah, I need to run first here. Then it will go through for each epoch, it will go to the 15,000 batch, 15,000 sample, right? 200 for each batch. And for this, you can see both training loss, training accuracy, and validation loss, validation accuracy. And you can obviously see that for the training loss, it always reduce. But for validation, it reduced at the first few steps. After this third step, the loss increase substantially until the end, right? That means the network stop learning at this stage. No, I should not use the word stop learning. I would say the network has become overfitted after the third epoch. Right? After the third epoch, it has already become overfitted. This is called overfitting, which we will take a look at it more closely in the next lecture when we learn about optimization. Alright, so once we got the history, a model fitting object, we can use this history to get the history and then plot the comparison between loss, validation loss, and the training loss. Training loss will always reduce, but it doesn't guarantee that the model is good. Right? Actually, the model is at the maximum. I would say it's already at the best at the third epoch. So we should stop at that point actually. If you plot the accuracy, you can see that the drop in the accuracy after the third epoch. Right? And for the training, you will always increase that. Right? So let's train only fourth epoch. And this would be by setting epoch to 4 and using all the trained data set. Then we can evaluate the result by running model.evaluate on the test set. And then you will get the result as the loss and the this value is the accuracy. If you want to show all the results like ROC, AUC, you can specify it in the matrix and then in the compile here. By specifying it as the AUC or the R-square integration, you can get the result of this using that. You can use the network to predict, to get the result, just use model.predict and then it will perform prediction out for you guys. Right? That is for the binary classification. Okay. Any question about the first one first? Oh, note that in binary classification, the activation of the output here is sigmoid. Right? Sigmoid means that you want to predict probability at the output layer. Okay. If no question, let's move on to the next one. The multi-class classification. In case that you want to do classification, but there are multiple tasks like this one. This is the Reuters News dataset. It contains the dataset of the text classification that you have a sequence of text that you want to map into you want to predict it into class. Say, let's take a look at this. Let's decode it. Yeah, right. This is the text, and the text is like that. That's it. As set as a result is the number acquisition of space code, it expected earning per share. So this is like the financial news. Then use the same vectorized sequence and take a look at the y. Y would look like this. Y would be the one hot encoding now because we want to predict in a multi-class manner. Right? Y would now be the one hot encoding of the class. And then we can create the model in the same way, but instead of having sigmoid, now we have softmax as the activation layers. Right? Everything same. But here the loss has to also reflect that choice. The loss has to also be the categorical cross entropy. Okay? And the same thing. Right, you can see, note that it now become harder to overfit. Right, all right. The validation error, validation loss reduce until you are about, the best one is actually at the epoch 10. Right, the best one is at the 10th epoch, which you get the best result. So here you can see that about something like 8, epoch number 8 or number 10, which is the best one. Then we can train the model again with the value that we got, get the best model out, and then use in evaluation, and you get the accuracy output at 0.99. Right, this is the near perfect classification. I use the right one, right? Yeah, okay, 99% accuracy. This is the result of prediction of test. You get this vector out and get like maximum argument of this vector will get you the result like here, np.arg max, and then result 0, I get it as the category number 3. You can take a look at what category number 3 is, and then now you have the perfect prediction. Lastly, you can use neural network to perform regression. This is the Boston house price data. Boston house price has the data that looks like this. This is the train data shape. These are the results, the train target. Let's take a look at the train data. Right? Train data. Right. Train data are in forms of vector. Actually, there are meanings, right? Each column can be number of bedroom, number of bathroom, the room size and authors. but it has already been prepared for testing in the Boston housing dataset. So to work here as a regression, you need to normalize the data, especially the trained data, right? Normalize it. This is the normalization of data into the z-score, right? By minus the mean and then divided by standard deviation. I have transformed everything to the z-score using the mean dataset, the trained dataset. And then you can build the model here by you can define the model building inside a function. Right. You can note that here the output does not have activation layer. The activation function specification means that the activation function here would be linear activation. All right, and then we also define the loss to be mean square error, and this is how you build a model. By having this function here, you can use this function inside a loop. Right? Prepare the data set, and then use the function inside the loop, and then fit the data so that you can perform cross validation by yourself by partitioning the data according to what you want. Oh, got to build a model. But well, actually the last step can be done using the cross validation capability of Keras as well if you want. All right, so let's wait for this a while, and then you get the validation error and MAE to know how best it performs in terms of the prediction of the values out here. Okay, so thing to note here is that for the regression model, if you have just like one output regression, you can just take it as one. If you have multiple, you can specify multiples. But you don't have to specify activation, or you can specify activation for the output to be linear, and that's it. Right. Alright, so this is how you use Keras to build the feed-forward model. This is quite straightforward. But we will take a look at this again in the next lecture on how you can control the optimization. We will take a look at the mathematics of RMS prop and the mathematics of the ADAM, the adaptive moment, to understand what matters in terms of the design choice. When you decided to go with one design, what would happen to your model? Right. We will take a look at that in the next lecture. And then play around a bit with this. But you won't see much. You see that a lot when you have like complicated data set. For a simple testing data set, these are very simple. Right. Not yet here. That's for number one. All right. So let's take time here to have questions. Can we use multi-class classification for binary data? For example, we define label 0 as 1 hot, like 10, and label 1 as 1 hot, like 0, 1. Let's frame it this way. You want to ask me whether we can use multi-class classification. So what I think what you want is like multi-label classification, right? Is that it? In the multi-label, you can have the vector like this one. Suppose you have 5 class, but you can have something like this. That means, for example, you want to tag whether this article should be in sport or in drama class. You can do it like this. And then for this one, you can choose to use say you can use event regression to do this job. But I will try to find a better actually let me open Keras to see which activation function would be suitable for this task. But you can do that. Yes. Let me take a look at the API first. Activation this value submax. multi-level classification. You just use sigmoid with multiple output. Yeah. So you should not use softmax, because if you use softmax, it would mean that you want to pick one out the rest. You can use sigmoid with the 5 output, and that's it, right? That should be it. Yeah, use sigmoid with 5 output nodes, and you can get this something like multiple binaries like that. Alright, we already get the result here. So let's take a look. The all score. These are the all scores of the cross validation. We get about 2 something, 2.4, 2.3 of the mean absolute error, comparing to the value of about 20. So we got error rate about 10% approximately. Alright, so this is how you can build the multi-binary class, multi-class and regression model, right? Classification and regression model using the feed-forward network. And there are plenty of combinations. Once you learn more about the architecture, you can see that you can use this to estimate age with the convolutional neural network. You can use this to do better than this one. You can see that we are handling the data in text to a format, but there's a better way beside the back-forward model like this one, like using sequential model in RNN. We'll take a look at that architecture as well, on how the mathematics of it work and also implementation. Right? Any other questions about model implementation? Could you explain why do we need to add bias B? Okay, sure. I think this originates back from when we do the regression, but it has a lot of merit in itself. The bias B, right? The bias B, why do we need that? Take a look at this one. By having this bias B or W0, it allows the network, the node here, to capture the data pattern with regardless to the background value. If the average value or the offset is like 100, if it's like 100, this weight can learn that offset, can learn that level, can learn that bias, so that it can say that W0 should be 100. And then the variation from 100 can be captured to the other W. Right? The same goes for linear regression. The y equal mx plus b in the linear regression, b is used to capture the bias, right? The intercept, right? In multiple regression, when we have the multiple x time with weight, the b value or the one that multiply with 1 is used to capture the offset or the background level, so that it kind of lifts everything up, and then you can capture the variation of the above, right? Let's say if you want to use regression to predict salary, right? Then salary maybe in terms of like 10,000. B would be something, the W0 here would be something like maybe 20,000 as the average, and then you can, or the 30,000 as average, and you can kind of going up and down from that, right? Using the other parameters. So that's the purpose of bias or B. And the same thing has been used in neural network to represent such a background activation. For example, background activation here can be used to represent the whether the picture is bright or dark, right, in the model later on that we use. Okay, which they will learn it by themselves, right? We don't need to specify anything, so kind of leave it at that, and then it will just learn it out. Bad thing about deep learning is that it's hard to explain, right? So it is very difficult to explain why is it working. So that's why there's a trend nowadays to have something like explainable AI, to make deep learning explainable, which is very active research. I would say it's just the trend that come up this or the past 1 or 2 years, that people trying to find a way to make deep learning more explainable. Okay. Can you call epoch as iteration? Sure. But well, epoch has a sound of something like evolution. It's originated. It is originated quite back then when they kind of proposed that this is related to human learning of the brain. So that's why there's this weird name, the epoch. Yeah, it's just like iteration. All right. Bias, isn't it for neutralization or normalization or fitting? No. Different things, right? The same word, right? Bias, and bias. The same word, two different meanings. Lexman said it is about neutralization, normalization or fitting. Yes, that's true. That means in terms of like the last lecture, the bias of the model. When you have more bias, it means that you manually specify the parameter yourself, right? That's one use of English, bias. But in regression, bias refer to bias or offset, right? I would say there are multiple terms: bias, offset, intercept, background, right? This refer to a value, or B refer to a value that you leave it as constant in the model, just like this x0 equal 1 and w0, just like which one? Yeah, just like C here, just like B here. These are the bias value or the offset value. Right? Let's call it offset then, right? But they are usually referred to bias because it means that whether this node will be biased to certain value or not. But yeah, they are like the same word, two different meaning though. Right? Be careful about that. I would not ask you what is bias. That's a promise for the exam. Right. Okay. Any further questions? Something about confidence interval when you completed prediction. Sorry. What do you mean by confidence interval? Do you mean confidence interval in something like the confidence interval in central limit theorem, or what confidence interval you are referring to, or do you mean the probability of the prediction, the accuracy, right? Accuracy. Let me check whether I have shown you this lecture already or not. I think it's in the review, but on the safe side, I will find the lecture here. Should be in the review. Let me find first. No, not in the review. Accuracy. Okay, maybe I have not mentioned it here, but let me share this slide. Let me share this one here. what is accuracy, right? When you perform classification tasks, um, you usually for the binary classification, you would have those that are actually the positive set and those that are in the negative set, right? If you want to judge whether your model is good or not, you can you can put the data into a table like this one. This is called a cross tabulation or the confusion matrix of the prediction result. Because you now cross tabulation between the actual label and the prediction. Say if you predict yes and it is positive, then this is called the true positive, right? If the model predict yes but it is not, then this is called false positive, meaning that the model alert but nothing happened really. And if the model predict no but it is actually no, this is true negative, right? Like model not predicts there is no, then it is actually no, this is true negative. If model predict no but it's actually positive, like the doctor screen you and then tell that you do not have COVID but actually you have COVID, that's false negative, right? So you can see that each of these carry different meaning. Accuracy is the calculation of taking true positive and true negative divided by all instant. This is called accuracy, right? So that's how accuracy is calculated. You get a positive or correct prediction dividing by the all divided by all instance. Then you get the percentage of how accurately the model predict. Alright, this is one way to assess the model, but there are other ways as well, right? Well, I would suggest a source that would be better. Let me check. I don't think the book has, because the course here, the book here does not really focus on the basic machine learning. It focuses more on the of the advanced stuff, advanced concept in that. Let me check if it has the concept, something like accuracy, precision, recall or not. Otherwise, I will post the result. No, I will post the slide. The slide that I have here onto the group so that you can use it to do something like referencing or others later on. Maybe let's do that. This is more research oriented, so they kind of lack of basic stuff. Let me check. Accuracy. No, it does not have any reference to that. Only have the reference to the concept of deep learning. So let's say I'm going to post this onto the group if you are interested in that. I teach it to the third year undergrad students, so it should be fine for you guys. Machine learning. And then I'm going to put that in deep learning class, additional, let's say supplementing one. If you want to, if you do not know how to create the model using Python, you can take a look at this slide. Should help. Next question is about exam. Whether it will include definition, I still do not know. It's still far away, final exam. Usually I don't really ask for definition. Because it's too easy, the exam would be just like, because I still think that there's still situation this year. So the exam would be in the class, probably should be written. So mostly I will ask you about the logic, about the design, rather than about the definition. Right? Definition is too easy, so we would not do that. So I'll upload the Python machine learning for you guys if you are interested in that. For that. Coding exam, every assignments are exam. That should answer the question, right? So if you ask me whether there are coding exam, you already have it every time that you do the assignments. No coding at the end because I don't see the points. You have to do it anyway for every of the assignment that you have. That should answer your question. We have about 5 of them. So think about it as 5 sub exam, right? Mini exam, doing the coding by your own. Okay. To submit the first assignment, handwritten image attached with the Jupyter role is okay. Yeah, it's okay. Do you share Kira's code to show us in the class? I already shared it in the group. I think if I did not put that into the wrong group, I should not have, right? I already shared that. Yeah, I already put the Python notebook in that. So you can take a look. It should help you doing the second assignment. Right? I will post the second assignment maybe in this week, in the next few days. It will be about building the deep forward network, doing the backpropagation, create your own Keras model. This will be easy one, right, to do the job. For every assignment that I give you, you can exceed my expectation to do more. There's no limit to that. If you want to do more, just do more. Then I will. But well, at least trying to fulfill the expected goal there. Okay. All right. I will just stop here. If you have more questions, feel free to post in the group. I will answer to your question as soon as I can. All right. Do you stand a chance to get A? Get A can be done by submitting the work on time, submitting the assignments, and you get A. Usually my class have about 10% of A for the undergrad. For the grad students, maybe if you kind of pass, if you pass the requirement, it should be fine. But there's no guarantee, depending on whether you can do the assignments, whether you can finally do the work, and you understand the paper that you present. Because as I said, there are 3 parts of the score that you need to accumulate. First one is in terms of the work that you submit. If you submit high quality work, it should be fine. Second one is the exam, right? Everything exam, just 30% of the work, right? If I remember correctly. I don't remember the percentage in the actual sense. So yeah, the second one is the let me check. Right. So assignment constitute of 50%. So the work should be good. Copying. Oh yeah. Plagiarism, copying, results in 0. Okay? Okay. All right. If I find that the work is just the plagiarism of your friends, they get 0. Okay? Final exams, that 30%. Okay? Research presentation, 20%. So you might wonder, what are the criteria of plagiarism? It's easy to detect, right? Just making the same mistake for every of that, and say something, structure the IPython notebook in the same way for everything. That's impossible. For all the code to be the same, like I said, because you need to write, you need to explain, you need to have your own take, and even the work you need to do it yourself. So it's hard to get the work the same as the other way, right? So that's the assignment, and the final exam is only 30%. And 20% for the research presentation, which you need to pick one paper and study it, think about it as literature review, and then present that to the class, right, about the deep learning architecture that you find. Right, you need to understand the work deeply, such that I ask you about the mathematical foundation that you find, that should be able to answer that, on the inspiration of the model that used in the paper. Right. I would say that because last years I got about almost 40 students, so I have kind of in a way review a lot of research paper in deep learning. So yeah, I think I will know what you pick up there. Okay, this is it. I think. Hope you submit the work on time. If not, let me know, but there will be penalty if you submit it late. The other class might not even allow that. So say try to submit it on time. That would be the best. If you cannot do the whole thing, just partial would be better than not submitting. Okay. Next, we will take a look at regularization of the network. Right. See you next week.